This video is part 2 of a series about the Continuously Variable Displacement Engine and Compressor Drive System. We will cover in detail how it improves fuel consumption through reduction of two major loss mechanisms inherent in fixed displacement engines. I would like to thank the Department of Energy's Office of Energy Efficiency and Renewable Energy Vehicle Technology Office for their financial support getting the CVD system designed, prototyped, and tested. To start with, the whole idea behind the CVD is to reduce part load losses. This is because most engines, particularly passenger vehicle engines, run at very low loads most of the time. Whether the fuel is gasoline, natural gas, or diesel, the engines have significantly less efficiency at low and mid loads than at full load. The optimum design would be an engine that always ran at full load, but could change displacement to match the power needed at any moment in time. Thus, the ultimate internal combustion engine for low load applications such as automobiles, light trucks, even many heavy-duty trucks, as well as load-following gensets and most industrial engines, would be a variable displacement engine that could maintain its compression ratio throughout the displacement range. Reducing the stroke of the piston does little good if the compression ratio is lowered. One of the most important features of the CVD is that by carefully choosing the geometry, one can keep the compression ratio constant as the stroke is reduced, or the compression ratio can be raised or lowered as the stroke is reduced. We have developed a simple spreadsheet representation of the geometry, which allows us to easily achieve the characteristics we want. As we can see from the chart, the clearance at top dead center on the left cylinder gets smaller as the stroke gets shorter, as shown on the right cylinder. We can see how the mechanism changes more clearly with these three cutaway positions. In 2012, Brad Tillich's company, InSim, ran GT power simulations for both the CVD and a conventional gasoline engine, including a weighted steady-state 10-mode federal test cycle fuel economy analysis. The effort was sponsored by Cummins, who also provided the test mode values and weighting. Both engines were 5.0 liter and used the same methodology for friction FMEP calculations. The FMEP calculations compared well to calculated values using the Haywood-Sandoval empirical equations. The engine simulation showed the CVD had 30% better fuel consumption than the conventional gasoline engine. At the time, a low-friction nutator anti-rotation device had not been invented, so the CVD friction was worse than the conventional engine at full stroke. Since then, a new method has been developed using an anti-rotation gear set, which has eliminated the high friction element. At the same time, it was estimated that if a low-friction anti-rotation device could be developed, the improvement would be another 5%, or a 35% improvement. Also important to note was the baseline gasoline engine was a basic gasoline engine. It did not have variable valve actuation or cylinder deactivation. It was not downsized with an add-on turbo and intercooler, nor did it have direct injection or a cooled EGR system for dilution. If the cost of the CVD and the baseline V8 were compared, the CVD would be more expensive because of the two sets of roller bearings. However, if it were compared to an engine with all of the aforementioned add-ons, it is estimated it would still be about 10% more efficient and would be far less costly. Over the years, there have been many inventors claiming similar fuel economy improvements from their designs, but have not been successful proving it. The question I always ask them is, what losses have you reduced or eliminated? No matter how beautiful or elegant the engine design is, if it doesn't reduce or eliminate a loss associated with existing engines, it is not going to improve fuel economy. The CVD is no better than a conventional engine at full load. It simply reduces losses much better when the power is reduced. Let's look at exactly how the CVD does that. This chart is a comparison of pressure volume diagrams of both engines running at low speed and low power consistent with typical driving. Gasoline and natural gas engines suffer the worst part load losses as they are controlled with the throttle. The throttle creates a depression in the intake manifold prior to the engine compressing the air. We engineers look at a part load loss called pumping loss, which is caused by the exhaust manifold pressure being higher than the intake manifold pressure. Pumping loss is significantly magnified by the throttle. The throttle vacuum makes the engine operate against an adverse pressure gradient. The CVD virtually eliminates this loss, as we can see by the blue area being smaller than the red area. Variable valve timing can be used to mitigate this to some degree, as seen by the darker red area being smaller than the light red area. Many engineers think of the pumping loss as the major loss caused by the throttle. While it is significant, it is far smaller than the loss caused by the reduction of pressure before combustion, which we will see in a minute. Here is a chart that is in all of our mechanical engineering and thermodynamics books. The Otto cycle is a thermodynamic representation of the spark-ignited gasoline engine, and the chart tells us the maximum efficiency of the cycle is a function of the compression ratio. Those engineers that like to pick nits will say it's not really the compression ratio, but the expansion ratio of the engine. In the Otto cycle, they are the same, which is not true of real engines. The red area is where today's engines run at their most efficient points near maximum torque. Mentally extrapolate this down to where throttle engines run at low loads where the real compression ratio is only 3 or 4. There is a huge loss caused by the throttle which often gets overlooked. We can see from this PV diagram that if the intake manifold is controlled to 0.6 bar vacuum and the air is then compressed, the pressure in the manifold is 9 bar, not 19 bar as it would be with a CVD. When the fuel is added and combusted, the pressure goes up similarly, but the endpoint is nowhere close to what it is unthrottled. Variable valve timing cannot overcome this and somehow restore the 19 bar compression pressure. It simply makes no sense to expand air, then recompress it, as you are downgrading the engine's effective compression ratio. But that is the limitation of fixed displacement. Even the BMW Valvetronic system cannot overcome this problem. This slide is the most important piece of information in this video. We're looking at the same PV diagram, but with the linear scale, not the traditional log-log scale. The dramatic improvement of the expansion ratio at this operating condition almost doubles the indicated efficiency. For the CVD engine, this is the mother load. Operating cycles such as Miller cycle and Atkinson cycle were created to get just a small improvement in the expansion ratio, nowhere close to this increase. But again, I want to emphasize that this benefit is only at part load. On the other hand, that's where most engines, especially automobile engines, operate most of the time. Later in this video, you will see an animation of the mechanism both stroking and also rotating. Most engine engineers will immediately think there is a lot of friction in the mechanism and assume that this is a fatal flaw in the concept. Certainly I would, seeing this for the first time. Actually, it's quite the opposite. The CVD significantly reduces friction, especially during part load operation, and it does it several ways. First, it uses rolling element bearings rather than hydrodynamic bearings. Rolling element bearings are difficult to use in conventional engines, as they must have fractured races for the main bearings and rod bearings to fit between the crank throws. In the interest of transparency, rolling element bearings are essential to the CVD concept. As the CVD moves to low displacement, the ratio of force transmitted to the bearing load goes the wrong way. If traditional hydrodynamic bearings were used, the high bearing load would represent a significant increase in friction loss. This is why we use taper roller bearings with ceramic rollers, which have very little friction even with high loads. Hybrid bearings, as they are referred to, are now mainstream technology. With a conventional crank slider mechanism, there is a side load on the piston caused by an angle between the rod and the piston motion. This is the highest friction contributor in the engine. There is also high velocity at the big end of the rod, converting friction torque to high friction power. With the CVD, there is virtually no thrust load on the piston and virtually no rod losses. The big end of the rod does not rotate about a crank pin, but barely moves as it connects to a nutator. The little end of the rod has even less movement, as the rod is almost always parallel with the cylinder, as can be seen in this cutaway. With a conventional engine at a given speed, whether at full load or 10% load, the friction is almost always the same. With a CVD, the piston speed is reduced, so the thermodynamics are similar to full load, just less mass flow. The reduced piston speed lowers the friction even further, as the friction power is proportional to the square of the piston speed. As I mentioned earlier, if you're going to improve fuel consumption, you must reduce the losses. This chart quantifies this precisely, as we see a comparison of losses of the CVD and the conventional V8 over the federal test cycle. The biggest reduction of inefficiency is in waste heat. The reason for this is the improved thermodynamic efficiency, or indicated specific fuel consumption. This is due to retention of the effective expansion ratio of the engine at part load. We also see that the pumping loss is almost completely eliminated and the friction power is reduced by about the same amount. The in-cylinder heat transfer is a little worse with the CVD due to the higher pressure at part load, increasing the convective heat transfer coefficient. One of the results I personally find amazing is that there is a 31% reduction of exhaust gas waste heat without a waste heat recovery device. Obviously, it's better not to create waste heat than to create it and try to recover it, which is difficult and expensive. Over the past several decades, there's been a trend towards electrification of powertrains, from hybrids, mild hybrids, plug-in electrics. In spite of the buzz, still only 2% of the vehicles in the US are electric. There is no intent to knock electric cars. Some, like the Tesla, are awesome, and they're getting better with battery advancement. But it appears the gasoline engine will be the dominant powertrain in autos for several decades. How are gasoline engines going to improve fuel economy to meet government mandates? A common strategy is partial electrification along with advanced gasoline technologies, of which there are no shortage as shown in this chart. What losses are these technologies trying to reduce? It is universal. Reduce the losses associated with throttling, not just the pumping, but low indicated efficiency, and reduce friction. Every one of these 7 technologies are trying to reduce exactly the same 2 losses. And none are 100% effective, or there wouldn't be a need for multiple technologies. Is the combination of all of them as good as the CVD? Debatable, but only a running CVD can end that debate. The CVD certainly has a significant edge in manufacturing costs and packaging. Here is ESI's vision of a gasoline roadmap. One reason that boosted downsize and dilution are upgrades to the CVD is because the variable stroke is not designed to reduce beyond about 25 to 30% of full stroke. A second reason is because the CVD is the only gasoline engine type that can use turbocharger boost at part load. So yes, boosted downsize plus dilution can improve the fuel economy of the CVD, but at a higher price point. This presentation has been fixated on gasoline engines. Of course, there are other fuels such as CNG, LNG, propane, and diesel. If we take CNG, LNG, and propane, they have the same basic problem that gasoline engines have. They are controlled by that wasteful technology, a throttle. Lean operation has been chased to try to eliminate throttling and recover engine efficiency, but you lose the ability to use the incredible 3-way catalyst. CNG, LNG, and propane engines will benefit from the CVD technology just like the gasoline engine. And for high power applications such as medium duty or heavy duty trucks, a turbocharger and intercooler can be added, plus cooled EGR to reduce maximum exhaust temperatures for increased durability and lower material costs. Diesel is really a different story since diesels are typically unthrottled. The CVD would bring much lower friction due to the roller bearings and reduced piston thrust load. Again, reduction in part load losses would be more significant than full load improvements. Reduced mass flows at low loads would eliminate ultra-high air-fuel ratio and thus improve the indicated efficiency by raising the combustion temperature. This would also have a significant impact on after-treatment efficiency, eliminating the ultra-low exhaust temperatures and also increased passive regeneration of diesel particulate filters. What applications would benefit from CVD technology? Basically, any engine that spends a significant amount of time at part load. I haven't listed long-haul heavy-duty engines here, but even these engines spend the majority of their time at part load. I'm going to wrap this up with a couple of short simulation animations. If you're interested in seeing more detail of how the CVD works, look online for part 1 of this presentation. It also includes some test video with the first prototype running. Now that there's a prototype that proves the CVD drive works, it's time to take the CVD to the next step and finish the development as an engine. I'm always looking for feedback and constructive criticism, so share your thoughts with me at steve@esi-inc.us.